Hey, so welcome to Math 331, the little questions. What I want to do today is I want to finish off, talking about the arithmetic mean, geometric mean inequality, because we haven't done nearly enough ways of proving it. And so again, it's an important identity. The reason we're doing so many proofs is because I want to talk about ways to prove things. And it's nice to be able to look at the same result from many different perspectives and ask, what does each approach give you? And so we've already seen one geometric proof using a result from geometry class that you have probably forgotten. And if you haven't forgotten, you might have had no idea why we ever would have cared about the product of this part of the chord times this part of the chord. Why do we care about stuff like that? Well, if we have various objects in triangles, we know the hypotenuse is larger than, or at least as large as either side. And that inequality can transfer into algebraic ones. But it's what's the best way to approach. I will also try to use results from another math class that you have taken. I don't want to say right now which math class that is because I don't want to give you a hint on what to be thinking about, but there is another way to approach the arithmetic mean, geometric mean inequality using a class you should have taken or at least placed out of taking. All right. Before we do that, I do have to just mention that there was a typo in the analysis yesterday, and I'm not quite sure if I'm allowed to say typo when I'm writing, but over here when we had the expression for simplifying the algebra, or when we simplify the algebra, we forgot to include the +1 from the s when we factored out the s. So the numerator should actually have a +1 over here as well. And we forgot that last time. So that changes beta a little bit, right? And so then the question becomes, what does beta become if we put in that +1? Well, let's just do the algebra again. Oh, interesting. It's not letting me erase this. Wow. Okay, we'll keep that there then, and we will just write the correction below since it won't let me erase. So what would we now get? We want that fraction to equal 1 over n, right? So we have 2 to the k minus n times beta plus 1 over 2 to the k equals 1 over n. So we can multiply both sides by 2 to the k. All right, so I am at least able to erase over there, okay. And so I would now get 2 to the k over n. I now subtract 1 from both sides, so I would get 2 to the k minus n times beta equals 2 to the k over n minus 1. So that'll be 2 to the k minus n over n. Oh, that's really nice, right? The 2 to the k minus n will cancel from both sides. And now, rather than getting that really bad expression for beta, we now get the much simpler expression for beta, that beta equals 1 over n. All right, so now this over here just becomes beta equals 1 over n. And that's going to make things a lot easier. So on the left-hand side, we still have the arithmetic mean. We've just rescaled things a little bit. Okay, and so now if we try to do the argument we had before, we had the arithmetic mean of x1, xn plus 1 dot 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 was greater than or equal to the geometric mean because we proved the AM-GM inequality when we had a perfect power of 2. And we're just cleverly choosing the values of the red x's. And so we then got the arithmetic mean by choosing beta to be 1 over n. And this is where I was actually a little bit careful and I wrote 4r beta. So 4r beta was correct. It's just beta is now not what we had before, but now the beta is 1 over n. So here we're using beta equals 1 over n. And so now we have the arithmetic mean of x1 through xn is greater than or equal to the product of x1 through xn times xn plus 1 through x2 to the k, and then we have to take the 1 over 2k root of that, because that's the arithmetic mean, geometric mean. Okay, well, we put in what we know for the values of xn plus 1 through x2k, okay, which is going to be beta times the sum. And the sum is the arithmetic mean times n. Oh, that's really nice, because now what does beta times n equal? 1. So we'll just get the arithmetic mean if we raise both sides to the 2k is just going to be the product of x1 through xn times beta times n, which is 1, times the arithmetic mean to the 2k minus n, because that's how many terms we had. Let me see if I can just copy the slide. All right, so I was able to copy the slide, but put it in the wrong spot. I'll fix that later. Not a big deal. Okay, so this is just going to equal 1. And so we have the arithmetic mean to the 2k is greater than or equal to the geometric mean. Well, it's not quite the geometric mean. I've got the product of the x's. What should I really have? To the 1 over nth root. But then I have times the arithmetic mean to the 2k minus n. So both sides have the arithmetic mean to the 2k, so I can cancel that. I can then bring the arithmetic mean to the negative n. Okay, well, I bring that over to the other side, and that's going to give me the, oops. So I'll get the arithmetic mean of x1 through xn to the nth power is greater than or equal x1 dot dot xn, which implies the arithmetic mean of x1 dot 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 xn is greater than or equal to the geometric mean. Just take the nth root of x1 through xn. So this is a really nice example of a strange kind of induction where we overshoot and then we fall back down. Instead of overshooting and falling back down, what could you have done?
Undershoot.
You could undershoot and try to build up. Which do you think is easier, to overshoot and fall down, or undershoot and try to build up?
Arbitrary build up.
Good. If we could have arbitrarily built up, why are we doing this? Right? If we can arbitrarily build up, then why am I doing this for powers of 2? So one thing is to see, can you prove the arithmetic mean, geometric mean directly? I was using the fact that for powers of 2, it's really easy to get it when you know it for 2, to get it for 4, to get it for 8, to get it for 16. Can you show that if you know it for n, you know it for n plus 1? If you can, there's no need to do this. So that's something to think about. Try to see if you can just prove it directly by induction if we don't have to do this. I might have done it this way because I happen to see that it's easy to do it for powers of 2. Once we know it's true for 2, we know it's true for 4, we know it's true for 8, but maybe we could have just slopped through and just done the algebra. Do you think it's better to, were we assuming things about the arithmetics versus the geometric? Yes. And so when we started to do our analysis, we were choosing things so that we chose the values of xn plus 1 through x2 to the k to be related to the sum. What else could we have done? We could have had them relate to the product. So again, go home and try to see, can you do the proof the other way? You know, for this proof, we assumed that it was something nice, that they were all the same, and they were just some multiple beta of the arithmetic mean. So the next thing is to see, well, what if they're all some, power of the geometric mean? And I would suggest probably a power rather than a constant times. I think it's a power would be the right way to look at things.
Can I just ask one question?
Yep.
When you went to the previous slide, one thing I had trouble following about the last lecture was that how you made that jump to xn plus 1 equals dot x2 to the k equals.
Because I can do whatever I want.
I understand that.
Yes.
What confused me was then when we come down, we say that, like, okay, we can, if beta is this,
If beta is now 1 over n.
1 over n, then we're saying that all of those xn plus 1 for x2 to the k, they just become the arithmetic mean of x1 through to xn. Like, we're just substituting in the mean of the sequence times n times. And like, initially for me, I was like, can we actually say that? Is that not like, is that breaking our rule in some way about, saying something for xn plus 1 through x2 to the k? Are we undershooting or overshooting the true value of that in some way by assuming this thing?
Again, as long as we're looking at 2 to the k objects, we can choose any 2 to the k objects we want. It's just what's going to be a useful choice.
Is it
And initially, we don't know what's going to be a useful choice.
right?
So to try to keep things simple, I thought, what if we made them all the same? And what if we made it so that each one of them is related to the sum? Rather than relating it to the sum, maybe I should have related them directly to the arithmetic mean, in which case beta would be 1, not 1 over n.
Right. I think maybe what I was, the conclusion I just came to then is just thinking about, because x1 through xn is just an arbitrary set of values. Like, you're
Yes,
saying it doesn't matter what they are. They
correct.
can be-
That's
they-
what we're given. That's what we're given.
In my head, I was like, oh, maybe they're smaller than the next set, but actually that's not the way to think about it.
Right, no. The way to think about it is we're given x1 through xn. We're not given xn plus 1 onward.
Right.
We have to choose an additional 2 to the k minus n objects if we want to use the result that the geometric mean, arithmetic mean inequality holds for some number of inputs.
Right.
And so we can put anything we want. What's good things to put in?
Right.
And if we make them all the same, then that helps. And then what's the natural sum? The natural sum is the sum of the x's that were given or the arithmetic mean of the x's were given, either way. If I had chosen each of the xn plus 1 and onward to be the arithmetic mean, then I would have beta equals 1. This is basically telling me I was not quite clever enough. You know, I shouldn't be choosing the x's to be the sum. I should be choosing the x's to be the arithmetic mean. That would have been a better choice. But because I had a free parameter, I can recover from making a suboptimal choice. Well, because xn plus 1 through x2k, they're all the same. We're choosing them all to be the same value. They could be any value they want. I'm trying to use the arithmetic mean, geometric mean inequality for 2 to the k inputs, where we've proven it, to then prove it's true when we only have n inputs.
I think I was in the same position you were about, like saying, like, yeah, but you know, we don't know anything about these values. Like, if we just say that they're all the same, like, how is it happy? Still
So here.
show that that's okay. But I think it's because
We're given x1 through xn. We are free to choose xn plus 1 dot 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 x2k, and then we can use the am gm inequality for 2 to the k inputs. So you're given x1 through xn, and you want to show the arithmetic mean of x1 through xn is greater than or equal to the geometric mean of x1 through xn. But we don't know that. We do know, however, that if we append a couple more x's, then the arithmetic mean, geometric mean is going to be true for that. And so in that situation, we know the arithmetic mean of x1, xn, and then I'll switch to the red, and then xn plus 1 dot 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 x2 to the k. We know that is greater than or equal to the geometric mean of x1, xn, xn plus 1 dot 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 x2 to the k. We know that is true. So we want to come up with good choices of the red x's so that this reduces and gives us the arithmetic mean of the first n is greater than or equal to the geometric mean of the first n.
So you're like it's overshooting because you're going. We know that it's true that there.
We know it's true when we have 2 to the k inputs.
But you want to do it.
We want to do it for n inputs. So we have to add some extra things. We can't use the arithmetic mean, geometric mean inequality, for instance, if we have 7 inputs. We can only do it if we have 1, 2, 4, 8, 16. We can't do it for 11 inputs. So what I can do is I can prove it for 16 and then choose, you give me any 11 numbers, then I choose 5 numbers appropriately. And now I can do it for 16. Remember, this geometric mean, this involves the power 1 over 2 to the k. And this involves dividing by 2 to the k. We're not dividing by n. We're not taking the nth root. So we have to do some algebra to convert from this inequality with 2 to the k inputs to the inequality we want with n inputs.
Okay.
So again, I strongly urge you to try to put in the details. If you had, you would have noticed that there was an algebra mistake, and no one had emailed me about that. So I know at least up to a certain time, nobody had tried it, or they had tried it and they were still working on it and didn't want to admit that they couldn't get it to work yet. But you really need to go home and try to fill in the details. Okay, so I'll let you go through, try to put in the details. We've proven it's true at powers of 2, and now we're talking about collapsing. We talked in class and just now about how we chose the values of xn plus 1 and onward to be nice for the sum. Go home and try to redo this proof, choosing the x's to be nice for the product. Make them all the same and choose them to be the geometric mean of x1 through xn to some power, and see if you can do a similar argument. That's the best way to get a sense of, do you understand what's going on? Try to do this problem the other way. There were 2 choices. Choose the x's in terms of the sum, choose the x's in terms of the product. Maybe we got lucky and we just chose the right way to look at things. Or maybe both ways work and one way is better than another. So let me try to do another way. Let's give some functions names. I will call a of x1 xn to be x1 plus dot 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 plus xn over n, and g of x1 through xn to be x1 dot 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 xn to the 1 over n, right? Hopefully you can figure out where these names come from. And maybe without loss of generality, we'll assume each of the x's is non-negative. And I want to compare the a function to the g function. Now, we talked about how these functions have nice properties, right? If we rescale, they're the same. So if we rescale the inputs, we rescale the output. So in what's hopefully obvious notation, a of r of x is just going to be r times a of x. Is everybody comfortable with just using x as an arrow to represent the input? And similarly, if we just rescale all the inputs, the geometric mean is just rescaled by all of that. So without loss of generality, what can you tell me about either a or g? What can I assume about a or g without loss of generality?
The x's are like.
So I could do that, but I'm talking about their value. What can I assume about the value of a or g without loss of generality? What does the value equal? 1. Is there any way that the value might not be 1? What's the only way the value would not be 1? So if it's 0, well, if the geometric mean is 0, what's the only way the geometric mean can be 0? One of the x's has to be 0, in which case the arithmetic mean wins. What's the only way the arithmetic mean can be 0? Everything is 0, in which case. So if either one of them is 0, we know the arithmetic mean, geometric mean inequality holds. So without loss of generality, we can assume is 1. Otherwise, the AM, GM inequality is trivial, as the GM is 0. Right? Is everybody comfortable with that? We're trying to prove the arithmetic mean, geometric mean inequality. This is a new proof.
Yeah, because I understand how, like, if the arithmetic mean, if it's 0, then it has to be all of them are 0.
Right.
If
If the geometric mean is 0, because the arithmetic mean has a bunch of non-negative items, there's no way the arithmetic mean can be negative because all the x's are greater than or equal to 0.
Then why does either one of them have to be
Well, no, I'm saying we can choose R appropriately so that we can rescale.
Okay.
If the arithmetic mean is 15, then divide every x by 15. And that reduces the arithmetic mean by a factor of 15, so it's now 1.
Okay.
So I can always rescale my variables so that either the arithmetic mean or the geometric mean is 1. Unless I'm in the case where one of them is 0, in which case there's nothing to prove. So without loss of generality, let's assume one of them is 1. You've got a 50-50 chance minimum. Which one do you want to make 1, the arithmetic mean or the geometric mean? Geometric mean. How many people vote for geometric mean? How many people vote for the arithmetic mean? How many people want to re-vote? Does this remind you of any class you've taken? We've got a constraint, we're looking at functions. Calculus, which calculus class? Calculus 3, multivariable calculus. I'm giving you a constraint. And given a constraint, I want to maximize a function. So if I constrain the arithmetic mean to be 1, and then I try to maximize the geometric mean, if I see the geometric mean is always at most 1, then I know the arithmetic mean beats the geometric mean. If I constrain the geometric mean to be 1, and then I try to maximize the arithmetic mean, if I see that, or minimize it, if I see that the minimum of the arithmetic mean is always at least 1, I know the arithmetic mean beats the geometric mean. This is a Calc 3 problem. Calc 3 constrained maximization, or constrained optimization. This is where you had, the constraint, say g of x equals c. You look for gradient of f equals lambda gradient of g. And that's going to be a system of n+1 equations, n+1 unknowns. The x1 ... xn and lambda. Lambda is the helping variable. We don't really care about lambda at the end of the day, but it helps us get to the right answer. And so the question is, do you want to have the arithmetic mean being the constraint or the geometric mean? And there's arguments you can make for both. Yeah.
Arithmetic mean is like much easier to take the derivative.
But we have to take the derivatives of both, right? We have to do grad f and grad g. So no matter what, one of them is the constraint, one of them is the function you're trying to optimize. Both of them you have to differentiate. So one of how many of you have taken real analysis? Okay, so in real analysis, one of the most beautiful theorems you see is if you have a continuous function on a closed bounded set, it attains its maximum and minimum. Which of these sets is going to be a finite set in space? The non-negative x's such that the arithmetic mean is 1, or the non-negative x's such that the product is 1? Which is going to be a finite space? The non-negative x's sum to 1, the non-negative x's multiply to 1. All right, so I'm hearing both answers. Why is multiply going to be bounded? The x is going to have to be bounded.
Not sure about that, but I think that sum should be infinite because you just go further and further. And
But so the sum has to equal 1, and the x's are non-negative.
oh, the non-negative.
The non-negative. So what's the largest one of the x's can be?
1.
Nope.
Oh, super close to 1.
Nope. We're looking at the arithmetic mean, say, equals 1. What's the largest an x could be? N, right? So if the arithmetic mean is 1, then the largest an individual x could be is n. What about the geometric mean? If the geometric mean is 1, how large could one of the x's be? It could be as large as you want. If one of the x's is 1 billion, what would the next x be? 1/billion. So I could make the terms as large as I want, right? So if I use the geometric mean as a constraint, I don't have a compact set to look at. So one question is, can you come up with a proof using this? So I want to make sure I get through a couple of things today. So I'm going to pause it here and leave this as an exercise for you to try to see if you can use your multivariable calculus to prove this. And then think, do you want to have the A fixed to be 1, or do you want to have the G fixed to be 1? One of the problems, and I don't want to do this again because it took 2 days for my hand to heal, you have to remember to check boundaries, right? And so when we're doing these constraint optimizations, these are for the interior points, right? If I give you a region, this is how you find the points. I'm sorry, these are how you find the points on the boundary. If you want to find the points inside, then you would just use the standard, the derivative or the gradient is 0. We know here that we don't have to really worry about the points inside, because to get inside the region, you would make one of the x's smaller so that the sum is no longer 1 or the product is no longer 1. It's enough to just do things on the boundary. So you can play these games over here. Here's another approach you could look at. Let's say we have x1 plus x2 plus ... plus xn, and let's say that equals s. And I can look at 2 things at a time. And so when I have these 2 x's, I could have a fixed sum for them. So what we're really doing is, let's look at the one-dimensional case, or the two-dimensional case. X plus y equals s. So this is one of my favorite problems. And I want to maximize x times y. Does everybody see that this is essentially the same as looking at the arithmetic geometric mean? What's the geometric mean of x and y? Square root. Okay, well, if I can maximize xy, that's the same as maximizing the square root of xy. Instead of looking at x plus y equals x, I could look at x plus y over 2 equals s, right? So if I'm fixing x plus y, it's the same as fixing x plus y over 2. So this is a very similar game that you can look at. This is the following problem, the Farmer-Brown problem. Anybody here ever read the book Click, Clack, Moo, Cows That Type? No one's read this? Oh, what a shame. So we will imagine that we live in a world where we care about cows. Given that this is at Williams College, this is not a bad assumption, okay? One of the reasons I teach here and not at other schools. We want to create the largest possible grazing area for the cows, but we're concerned about budgets. And so we want to use as little fence as possible. Does anybody have any idea of what shape is the best that will enclose the most area for the least perimeter? No. Circle. So the circle, it's a beautiful result that the circle encloses the most. The proof is a little bit involved. So what we will do is we will only consider regular n-gons, or actually we'll only consider n-gons. And then to be even simpler, we will only consider rectangles. So the question is, what rectangle will enclose the maximum area? And if you look at it like this, how would you interpret x plus y? Half the total perimeter. Does anybody know the name for half the total perimeter? It does have a name. Nope, close. Yeah, semi-perimeter. That's why I'm using the letter S. I'm not using S for sum. I'm using S for semi-perimeter. So we want to maximize the area given the semi-perimeter. And so we want to maximize xy. This is a multivariable calculus problem, right? This is a constrained optimization. You can do Lagrange multipliers. But we can also reduce this to a one-dimensional problem. How can I rewrite x times y as a one-dimensional problem?
In terms of x plus y.
Right, and so what do I know about x plus y? It's equal to s. So what could I call my function? X times s minus x. And so I have to check how do I find out where this function is maximized? How do I find where f is maximized? Take the derivative. All right, so I've got take the derivative, find the critical points. I'm waiting. And the boundaries, right? It took 2 days for my hand to heal. I don't want to do this again, right? Check the boundaries. So how do I find the derivative of f? Good. So the patron saint of mathematics, according to me, is Henry David Thoreau. So strongly urge you to read some of his writings. I have jogged around Walden Pond. He spent a year there, wrote a very influential work. And one of his big pieces of advice, does anybody remember? So you've made it when your name becomes a verb. So we Thoreau it. Simplify, simplify. Which could, of course, be simplified to simplify, but then it doesn't have the same impact. So if we expand this out, you get f of x is x times s minus x squared. And now rather than using the product rule, I can just use the sum rule, which is a little bit easier. So we get s minus 2x. Therefore, the critical point is x equals s over 2. And then the boundary points are x equals what? 0 and s. So f of 0 equals 0, f of s equals 0, x equals s halves equals y is the max. Could this be the minimum value? Is it possible I found the minimum value rather than the maximum value?
Yeah.
No, because as long as s is not 0, then we know it's bigger than.
We know that's bigger than at the boundary points. And from the result from real analysis that I mentioned, we know our function attains its maximum and minimum value in a closed bounded set. When I take x equals s halves, this is not going to be the minimum, this is going to be the maximum. If you were concerned, how could you determine if this is the maximum or the minimum? Second derivative test. Or what else could you use? Instead of the second derivative test, you could use the
Just you take the values just outside.
So instead of the second derivative test, you could use the first derivative test. And you would see if you did the first derivative test that the derivative is positive coming up to s halves and then negative beyond, so it has to be a maximum. So if we look at f of x equals x times s minus x, f prime of x was going to be s minus 2x, f double prime of x is going to be negative 2. This tells you it's going to be a maximum. If we plot x and if we plot f prime, here's s over 2, we see that the first derivative, if we are less than s over 2, the first derivative is positive, 0, and then negative. So that means the plot has to look something like this. So this is just basic curve sketching. If you know the sign of the derivative, you know if the function's increasing or decreasing. So we know the maximum value is going to occur at s over 2, and we get a square. Okay. This is actually related to the arithmetic mean, geometric mean. So we now know if x plus y equals s, then the maximum area is when x equals y. And so what would that area be? The area is, what will it be? It would be x squared. But if x equals y, what would that be in terms of s? S squared over 4. But s is related to the arithmetic mean. Right? So we know x plus y over 2 is equal to s, or x plus y over 2 squared equals s squared over 4, which is going to be greater than or equal to x times y, or the arithmetic mean of xy will be greater than or equal to the geometric mean of xy. So I'll let you put in all the details, for this, but we just showed that the maximum is going to happen when x and y are equal. If this bothers you a little bit, just keep s fixed. And if you keep s fixed, we see that as we vary x and y, if they're not equal to s over 2, it's going to be less than s squared over 4. So just by keeping s fixed, this gives us the proof. All right, there's two really nice things we can do from this. One is consider x1 plus x2 plus x3 plus ... plus xn, and let's fix that to equal s. When is this maximized for x1 equal x1, let's say xi greater than or equal to 0, without loss of generality, we can say s equals 1. What do you think must be the case for this to take on its largest value? We just did the case when we had two things. With two things, when is it largest? When they're equal. What do you think must be true to be the largest when you have n things? They're all when they're all equal. Imagine two things weren't equal. Well, if those two things aren't equal, we can keep the sum constant by switching them. So without loss of generality, if two unequal, say it's x1, x2. Consider now x1 plus x2 over 2 plus x1 plus x2 over 2 plus x3 plus ... plus xn, and that's still going to equal 1. So I haven't changed the sum, but I've made the product better. Because we just showed that the product is largest for two things with the same sum when they're the same. And so if I replace x1 and x2 with their averages, I haven't changed what they sum to. It still sums to x1 plus x2, but now the product will be better. So the largest product has each xi equal to 1 over n. And so I'll let you put in the details to prove that this is another way to prove the arithmetic geometric mean inequality. There is one subtle point that you have to be careful about that I will leave you to ponder. We don't necessarily know that things converge. We know that if we have two things that are not equal, if we replace them with their average, we make things better, right? Maybe we end up getting some kind of loop. So you need to somehow, and this is where real analysis becomes important. And that's not a prerequisite for this course, so I'm not going to go through the details here. All always happy to meet with people and talk about this. We know that if you don't have everything equal, I can always make something better by replacing two of the objects with their average. But maybe there's no maximum value. Maybe it goes off to infinity. This is where we need that result from real analysis, that there has to be a place where it's maximized. And if they're not all equal, I can find something better. So the only place it can be is when everything is the same. So you do need some real analysis to finish. Okay. So we talked about Farmer Brown. Farmer Brown has a brother, Farmer Bob. And Farmer Bob lives by the ocean. And so Farmer Bob has a fixed amount of fence. And he wants to maximize X times Y. Do you think you could solve this problem? How would you solve this problem?
Go back, same way we did it before with the other farm.
Okay, so what function would you get? So f of x would be x times what?
X times, or instead of y, we substitute for y from the first equation. So x plus 2y is this, so then y is s minus x over 2.
No, sorry, x. It would be
Well, yeah, minus x all over
so
2.
x minus s all divided by 2. Yes. And then we just play the same game as before. So does everyone agree that in principle this is not so bad? Who here knows their DC superheroes? Okay, most famous DC superhero affiliated with water. Aquaman. So imagine at the same time Farmer Bob is building his pen for cows, Aquaman is building a pen for fish. Do you agree that whatever is optimal for Farmer Bob, the mirror image is going to be optimal for Aquaman? So instead of considering S units of fence, we can consider the fact that we have 2S units of fence. What is the optimal shape going to be? Square. So the combined optimal with 2S of fencing is a square. So 2y equals x. So again, you can do the math the long way, but here's a high-level way of seeing that the optimal has to be a rectangle that's twice as long as it is wide. All right, we have time for one more proof of the arithmetic mean, geometric mean. This one involves infinitely fast dogs. And so I have actually met the person who owns the dog, and I actually met the dog before the dog died. So this is from Tim Pennings. And the question is, do dogs know calculus? So imagine you're in the water and your dog is next to you and you throw a stick. What path does the dog take to get to the stick? You're in the water. I mean, what path would the dog take to get to the stick? Just go straight. What if I threw the stick here? What path would the dog take? What if I throw the stick all the way down here? What path would the dog take?
Would it go to land?
Why might the dog go to land?
It's faster.
So if you're faster on land than you are in the water, it may be worthwhile to take a hit, run, swim to land, travel quickly on land, and then go back into water. And so what the path will be, and you might have seen this in physics, is something like this. As the speed on land gets faster and faster, what do you think happens to the path?
Sharper.
It gets sharper. And so imagine the dog travels infinitely fast on land. What path would you take? Straight down. So the infinite dog, so infinitely fast on land, you would now have the ridiculous situation where the dog would go straight down and then come straight back up. And at some point, it's better for the dog to do this than to swim directly to the stick. Do we agree that if the stick is close to the dog will just go straight to the stick? So if I look at the distance between where the dog starts and where the stick lands, at what point is the dog indifferent to swimming straight for the stick versus going to land? What should the length of the green line be? X plus y. And so if it's at x plus y, the dog is indifferent. As soon as that green line is greater than x plus y, the dog will go to land. All right, well, the whole goal of today is geometry, or at least it is right now. So let's look at, wow, that's a really bad straight line. I'll claim it was the currents. All right, so let's look at this right triangle. What can you tell me about the height of this right triangle? Y minus x. And so how would I determine what L is? Well, this is Pythagoras. X plus y squared equals L squared plus y minus x squared. So when I expand everything out, I get x squared plus 2xy plus y squared is L squared plus y squared minus 2xy plus x squared. And in a massive amount of cancellation, the y squareds cancel, the x squareds cancel, I bring things over, I get 4xy equals L squared, or L is the square root of, I guess, twice the square root of xy. When you look at this triangle, what can you tell me about the hypotenuse versus any of the sides? What relation do I have between the hypotenuse and any of the sides of the right triangle? Greater than or equal to. So we have x plus y is greater than or equal to 2 square roots of xy. Can you get the arithmetic mean, geometric mean from this? So you now get x plus y over 2 is greater than or equal to square root of xy. This is the geometric mean of xy. This is the arithmetic mean of xy.
Where did you come across this?
Just reading good math articles in good journals. There's a lot of journals that are geared towards expository articles. If you can't get the article online, let me know and I'll send it to you. Absolutely wonderful. And the dog really knew to do this. The dog really knew to take the hit. There's a lot of things in life where you do at every moment in time what is best. I would love to believe that if you had your choice of anything you could do from 10 to 10:50, Monday, Wednesday, Friday, it would be coming here to do Math 331. I would love to believe this is your ideal of how to spend 50 minutes every Monday, Wednesday, Friday. And I similarly would love to believe that you hold my other esteemed colleagues in a similar vein, and that's why you do all the classes and all the homework. Why do you do all this stuff? It's hopefully to get you to a point where you can do things in life that you really love. If you party all the time, you're not going to be able to sustain that. And so it's trade-offs. You can't always do what's best at every moment in time. Sometimes you have to take a hit to prepare yourself for later. I really don't want to study for this ACT or SAT test, but by getting a good score, that will help me get into a good college, which will help me, and yada, yada, yada. And so what we see here is the principle that what's best locally is not always what's best globally. That is a wonderful lesson to take from this, that locally best decisions do not always extrapolate to globally best. So that is a good place to end today. Have a good weekend all.